Yeah, I know, but like, still, if you're gonna buy writing for that, just bring your own thing. Why do you have it? I know you're like onward there, but I'm gonna buy. Why do they need to buy it for it? No, I don't know.
Okay, folks, welcome back. Happy Friday.
Makes no sense.
So let me remind myself of how this goes. So next week, I don't see your other part of your group at all live. So I'll see you again live in 2 weeks, basically, is how it's going to go, I think, right?
Yeah.
Okay. And then after that, I think you're on your practicum.
Yeah.
For 2 weeks. Wow. Okay, so we're kind of running out of physics, but we're doing pretty good. Yesterday, you guys did a good job on solving a series circuit. You found everything. You found the resistance, you found the voltage, you found even the volts in the various resistors. So that went really well. Today, we're going to look at the other type of circuit, which is called a parallel circuit. And if we get to it, we'll try a combination circuit and see how that works as well. Let's see if I got some folks online. I do. It's Ethan. Good morning, Ethan. So here we go. That is swell, and I'm sure we'll get some others as well. From yesterday, question about, check your notes out. Find your notes, and then you can see this with a picture. The current in a series circuit. No matter where I point in that circuit, what's the case about the current? Good. Lots of hands. Devante? It's the same. Good. Why is that? In simple words, why is that? Why is that, Isaac?
Because like in the series circuit, when you have resistors, the voltage accounts for the resistance and current, so that the current is always the same, always pushing out the same amount of electrons.
Yeah, but it's easier reason than that. You're going about it through the real back door. Let's just go in the front door. It's a lot quicker. So with a series circuit, why is the current always the same? Why is it always the same? In other words, Devante. Super. There's only one way. There's one, we say, pathway, and that is it. Exactly right. I want to correspond that with a parallel circuit now. Okay. We're going to draw one, then I'm going to do a little analogy here in the classroom. But first, I got some other folks to check in. Exactly, we're doing parallel circuits today. Ethan has it. And in addition to Ethan, I've got Isabella. Hello. Huge. Okay, so let's begin. Parallel circuits. And
Still don't even know
okay. And how about, hey, Jack, why don't we have you here? This has worked really, really good. But I know you can do better. It's a little more separate from a little social distancing. That's good. Thank you. Okay, draw me a parallel circuit in the air. How about proceed? Draw me a parallel circuit in the air. What's it kind of like? Okay, that'll work. You did two. I'm going to put 3 parallel lines in proceed. So he's got, I'll put in a power source as well. So if you did like that, I'm going to put in a couple of resistors as well. And then he did another line like this. And then he did another line like this. Well, I'm going to do a third line. You do 2, I'm going to do 3 just for grins. Oh, by the way, shoot, before I forget. Okay, I see you guys in, in like 2 weeks or a week and a half on a Monday, right? And it's Monday, I think, the 7th of June. Does that sound about right? We're going to do a lab, an actual lab, not in here. So can you put in where to show up on that Monday? I see like what, 5th periods on Monday, is that right?
Yeah.
Okay, so write or put in the class chat somebody. So, and it's your group that'll be here again, I'm pretty sure. So on that Monday, June the 7th, lab in W201. So I'll be waiting for you there with all the physics lab stuff, okay? So just come to 201 on that day to get to an actual lab. I'm gonna have you build and test a bunch of circuits. So if you did that before, this will be a great review. If you've never done it, it'll be, I hope, kind of cool for you. I got a couple other folks here. Good. Hello, Sina. Hello, Aaron. Yeah, so we got parallel circuits. All right, let's see. Can they see it as well? I hope. Yes, they can. Okay, so with a parallel circuit, let's finish off this. I gotta have a plus and minus here. Let's follow the electrons. Okay, so electrons are coming. How about Jack? They're coming from which side? The electrons are going, Jack, towards which side?
I believe the negative to the positive.
Exactly. All right, so let's have them go out this way. Think of like a mouse going in a maze. Okay, but what's going to happen right here? The electrons get to the spot. What will they do there? Inessa? They're going to split. And we don't know if it's half or what, but some are going to go this way. Some are going to go this way. All right, here they go. Now they get to this spot. What's going to happen at this spot? Alexander.
It's also going to go with the one and then here, one and then
Exactly, good. So then, let's follow this one going around. What happens then at this spot? Or what's sort of happening there, we could say, Felix?
The other electrons joining with them.
Yeah. Now these guys get together, and finally to finish it up, Felix, what's happening here and then to the end here?
Also, the electrons are joining.
Okay, got it. What's not the same throughout this whole circuit? What's not the same everywhere? Anton?
The current.
The current, exactly. Anton, you had a question too, or was that your observation?
No, I
Okay, all right. We don't know how many electrons are going here. If the three resistors were all the same, then it would be probably a third. But let's not make them all the same, because that's not always the case. Let's just put in some numbers here. I'm going to say like 10 ohms, 8 ohms, 5 ohms. And if they're different resistances, they're not going to be the same, but it doesn't matter. They all end up back going here. So here I have the total current, wouldn't I? And then it would split up into 3 parts, however many are in each part. And then they get back here and it'd be the total again here, wouldn't it? Once they all get back together. That's really, if you understand that, you've kind of got the idea of a parallel circuit. Split up, come back together. Why is it good if our homes are wired in this sort of circuit? Homes or apartments or whatever. Why is that good? Alexander?
you have to turn on everything at once.
Yeah, what if I had my wash machine here, then even if that wasn't on, the electrons could still go through what? 2 other pathways. You can call these, by the way, if you talk physics, you can all call them pathways or branches, like a tree. So you know a physics way to speak about this. So I've got here 3 pathways or branches in this parallel circuit. Right. We're going to analyze this. I'm going to put a number of volts up here. Let's say this is I don't know, 60 volts up here. Now here's the weird thing about this. Remember, in a series circuit, the heating was the same everywhere. A series circuit, Jack,
Alright.
The current, thank you, was the same everywhere. That's not the same here, but there is something that's different here. Watch this. Drop in energy. Drop in energy. Drop in energy. All three branches, weirdly enough, have the same voltage. So that's the same throughout the whole parallel circuit. Now I want you to think of a waterfall, okay? Here's the waterfall. It's going from here to here. And the waterfall has three parts to it. But they all have the same height. And that's like here. I got energy going here, 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 and it's all 60 volts. So unlike the series where I had to do like, here's my waterfall for, I'm sorry, they can't see. Here's my waterfall for the series circuit. Here it is for the parallel. It's all the same. It's all the same voltage. So that's the analogy you can kind of think about, okay? All right, what that means is, it means we need to start asking some questions. Here we go. So find the total resistance. RT, we say in physics. Find RT, the total resistance. Second thing, find the IT, the total current. We did that yesterday too. And then finally C, we're going to ask similar questions to yesterday. We're going to find V and I in each resistor. Okay. Let's see if I got anybody else there. Look at that. And they were all saying that. And Sina said things were split. The energy was split. She's right. And I'm sorry I didn't see that, Sina. Okay, I also got Hannah there this morning. Good. Welcome, Hannah. Thank you for joining us. And I got everybody down. That is super good. So here we go. For the first thing this morning, finding the total resistance, A, R2. Well, how did we do it in the series? What did we do, Jack?
We added all the.
Yeah, all of the
Yeah.
what do we call these guys? Each one is called, you remember, Leo?
Resistor.
Resistor. So we added the three resistances, okay? Or four, however many you got, doesn't matter. Here's the formula in parallel. You ready? It's one I don't really talk about much because it's pretty weird. I can't get RT, I get 1 over RT. And that equals 1 over R1 plus 1 over R2 plus 1 over R3. Whoa, weird looking. And I'm going to call this 1, 2, 3. To get this, you're going to use a math called calculus, which we don't have yet. So I'm not going to worry about this today. This is one of the few formulas where I just give students and say, here it is. Okay. Okay, we're going to use it. All right, so drop me in the numbers if you're following what I'm talking about. All right, drop me in the numbers. Devontae, so what are we doing here? 1 over 10 ohms. All right, keep going. Yep. Thank you. To solve this, we're going to make our life easy. Now, some textbooks have them find a common denominator. No, don't do that. That's a bunch of crap. All you do is change them to decimals. That's what we do in science. So here's what I mean. This side is still 1 over RT. I can't change that. But what's 1 over 10? Give me the decimal for that. 1 over 10 is what decimal? Oh, come on, everybody should know that. Alexander.
0.1.
Thank you. So 0.1. I'm going to leave off ohms for now until we get a little further. The other two you may have to punch out. 1 over 8, I don't know that. It's point something or other. Can somebody grab a calculator? Jack has one. Can you do 1 divided by 8 and give us a decimal, Jack? It's like point one something or other.
1.25.
Point 125?
Yeah.
Thank you very much.
Yeah.
What about 1 over 5? Somebody might be able to do that in their head. What is that, Isaac?
0.2.
Yeah, 0.2. So let's add all that up. You can do that mentally, can't you? 0.1 plus 0.2, 0.3, and then add this. You got it. Somebody said already. So it's 1 over RT equals 0.425. Is that right? Okay. Now I'm going to teach you a math trick. Anytime that's still not the answer, is it? Because I got 1 over that. I could do cross multiplying and all that crap, but I got something even easier. We're allowed in math class to put anything over 1 out. Because it's just divided by 1 is the same thing, right? If you do this now, you can flip both fractions. I'm going to just say reciprocal. You ever heard that word?
Yes.
Means like fraction, and then I turn it upside down. So turn them both upside down. So watch this. Now I got RT over 1 equals 1 divided by 0.425. And now, my folks, can you divide that? I need the actual answer for that. So what is that? 1 divided by 0.425, and then we're going to kind of round it. Jeff, what'd you get?
2.3.
2.3, is that the same you got?
2.4 would be more actually correct.
So like round it? Okay. All right, 2.4. And
5 is round up.
And we really do have now what label on the final thing. If it's resistance in essence. Ohms, right. Now, anybody else there? Oh, I got another one. I got Ayala. Good morning, Ayala. Thank you for being there. Okay. Here's something weird until you think about it. Look at what we got. 2.4 ohms. Look at those separate resistors. 10, 8, 5. What do you notice about the total? How is that, Isaiah? How's that compared to these other numbers? More or less same? Just tell me. 10, 8, 5, 2.4. Similar, come on, man. Is it more or less than these other ones? Smaller. Okay, that's important. Because I want all of you to understand why. Why is it less? Why is it less? Can somebody answer it by looking at the circuit? Why does it make sense it should be less? Well,
Because it can go through multiple paths, so it has more space, so it's less turns.
yeah. Yeah, exactly. It's got multiple paths. Let's say I'm trying to go over to the window behind Inessen. Or you can imagine this as cars in Berlin trying to get somewhere. And I want to go through the middle first. But some of you are getting out and it's really crowded. And so I'm like, oh, okay, well, maybe I'll take another path. Maybe by the window there, by Devante. Or maybe I'll take another path, go this way around past Isaac and Felix. Or maybe there's not just me. Maybe there's a bunch of people standing here that want to get over there. What's going to be more difficult? If they all take the same path or if they split up? What'll be harder?
If they all take the same path.
Right. So it's actually easier if they split up and take different paths, right? If they take different paths, would there be more or less resistance? Less resistance. Makes sense, doesn't it? So now do you see why that? So if I got more paths, the total is always less than any of the three in the diagram. because it's easier. There's more pathways to get over to another spot. Here, there's more pathways to get what? Here. I can go through that one, or that one, or that one. So I got less resistance. Okay? That's important. I hope we understand. Yeah. Okay. Yeah. Okay. So here we go. Let's write just a little comment. RT is less than all the other R's, all the separate R's, because if we have many pathways, let's say what it is now, the electrons have less resistance. And I'm going to pause here and take questions, comments. Isaac.
If you kept adding more and more and more pathways, would there be a limit at some point?
Yeah, 0. Like if I had more and more stuff, which I could, especially if I have it in like a home, then my ultimate limit is I can't get below 0. I can't have less than 0 resistance. But I can have really low resistance. Now, to be honest, in your home, that's a problem. If I have too many things running at once, I'm going to use a lot more watt. If I have a lot of stuff running, well, I'll use a lot more watt anyway. If I have many things running at the same time. A lot more current, electric current. I can start to use too much, so that then in this little box, they call it circuit breakers, I'm gonna have a switch go like this and turn off. Oh, and it means the person's using too many amps, too much current. It's a safety device. Because ultimately, Isaac, if I go pretty close to 0, that's not necessarily good, because if I use a lot of amps, what starts to happen to the wires? They get hot, and you don't want them to get hot. So
Fire hazard.
yeah, it is. It's a fire hazard, and if nothing else, it's a big waste of energy. You lose a lot when you really heat them up. Exactly. Good. So that was all number 1. I got to tell you, B and C are pretty easy, but A is the hard one. Questions about A? We kind of understand what to do. Change it to decimals, add it, flip it, and then just think about your answer. Okay, let's go to B. B. I want I2, the total current. Yeah, what can I use? It's an equation I taught you last time. It goes with a little rhyme, and I hope you'll never forget it. Good, I got 4 ends already. Somebody at home, what could I use that I taught you last time to get the current? A nice equation. How can I get the current? Felix.
I equals V over R.
You got it. So twinkle, twinkle, little star, V is equal to IR, and Felix has already solved it for I. Let's see if somebody on the internet has that. Not quite yet. So I was what again, Felix?
I equals V over R.
Okay, and that sounds great. So for this one, we're going to call it V over RT, because we got the total from part A already, and that's what we're going to use here. So let's shove that thing in. So I'm going to put it over next to it, so I got a little more room. And the voltage, drop in the numbers, Corsine. So what am I putting in?
60 over 2.4.
Yeah, 60 volts and 2.4 ohms. Okay. We're going to get amps, Corsine, out of it, yeah. Okay, can you guys divide that, please? 60 divided by 2.4. Let's see what we get. Anessa, what'd you get? 25?
Yeah.
You get the same thing? Thank you, everybody. That's a lot of amps. Can you see, because the resistance was so low, there's a lot of current flow. Maybe not as much in each branch, but altogether, man, 25 amps is really a whole lot of current. Good. Questions? Let's see how folks at home, hey, they got the same thing. Good, nice to know you're following. Thanks, Sina. Thanks, Aaron. They both got 25 amps as well. Let's go to C.
Oh, I thought that's ridiculous.
Good now. So there's my question. One of these we can just answer straight away. Which was it we talked a couple minutes about? It says find V and I in each resistor. Anton, you remember? Yeah, super. Good, Anton. So V is everywhere the same. So V1 equals V2 equals V3 equals the V total equals 60. Because I got all three use the same drop in energy. Bum, bum, or bum, it's always 60 volts. That part's the same for a parallel circuit. Oh, that was easy. Now let's go back and find the other thing they want is they want I in each resistor. And that's not going to be the same. Just in simple words, why? Why won't I be the same going through each resistor? Why won't I be the same? Devante? Yeah, yeah. And we said, although the total current was 25 amps, what's going to happen to that number, so to speak? Matthias, the total is 25, but what's going to happen if I got three branches? It's going to get smaller. It's going to split up, isn't it, into three parts. So let's find those parts, all right? Here we go. Let's get I1. So I1, and it's pretty similar to the formula that Felix gave me earlier, but now it's going to be what? V over slightly different here. Can you guess, Jack? Not RT, but what?
Which are
Well, which one of the R's though?
one.
R1. So now we're going to just do each one separately. Let's put the numbers in. It's still 60 volts on top. And R1, Isaiah R1 was which one? No, that's a total. What's R1 from our diagram? Which resistor is that one? 10 ohms, right? And we can do that mentally, folks. 60 divided by 10? Okay, and 6 what? Pigeons, bunnies? Amps, okay. Labels, I hate to be a pain, but we've got to do labels, okay? Let's do I2. Almost the same equation, isn't it? Okay. Throw the numbers in for me, Leo.
60 and 8, 60 volts and 8 ohms. So
Super,
7.5 ampere.
And you got it punched out over what you got?
Yeah, 7.5.
7.5. There's two ways to get I3. Before we do it, can someone guess the two ways? Inessa? All right, I could do the same formula, and then what's another way?
You can subtract the other two currents from subtract it.
Yeah, from the
total, yes.
From the total. Yeah, I'll label that IT. How about that? That was probably dumb on me. I should have put a T there before. Exactly, Nessa. So look at that. The three better add up to 25. So that's one way to do it. Or we can do the formula. I'll do both just to check it out, all right?
Yeah, there's a slight discrepancy because one of them is rounded.
Yeah. Exactly. And there will almost always, Leo, be a slight discrepancy within about a 1% or 2%, and that's okay. That's okay. But it's good that we realize that. Okay, and this was, what was our third one? We got last year. 5 ohms. Oh, we did that in our heads. What is that, gang?
12.
Good. Pretty sharp this morning, folks. I'm happy about that. Okay, so 6 plus 12 is 18 plus 7.5. 25.5. Okay, so we're up by 0.5. Okay, that's pretty close. Okay, or if we did the Inessa other method, we could just go 25 amps minus this quantity, 6 plus 7.5 amps. And we get like 11.5, something like that. So the two answers are pretty close, right? It's because of rounding. And ultimately, it's because the numbers I gave you, 5, 8, 10, are not very accurate. That's not very accurate. You'll learn more about that. If I did 10th grade, I'll teach you about rounding. But these two answers, if I round them both to a reasonable amount of spots, are basically going to give you the equivalent thing. Good. Same formula. Exactly, Aaron. 6. And look at that. Everybody's been following. Cena had it as well. 60 volts over 10. Thank you, everybody, for following at home. Looks like you're doing just right. Questions from you folks? You're doing good. Boy, the brains are really turned on. Let's have you guys try one. Ready? So we're going to try the same 3 questions, but I'm going to give you a different diagram. Same for folks at home. So, find blah, 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 blah. That's the same. I'm going to erase so you got some room. And hopefully we have time to put these up on the board, but let's give you some stuff real quick. What's the voltage here in Germany? I'll put that up at the top. You remember, Matthias, what it is here in Germany? Blah, blah, blah volts. What is it here in Germany? No, the one, you're gonna do a different one, but I'm just asking, what's the voltage here in Europe? It's what, Jeff? Thank you. So let's let that be this. So let's say it's a real German circuit here. And for the ohms, let's just change it and give you 22, 25, and 21. Okay? All right, so same 3 questions. Go ahead and work on it. I'll come around if you get stuck. Okay? Try and do it like we did the last one together, the parallel one together. Then we're going to have somebody put them on the board. Folks at home also work on that. We'll see what you get for answers. And then we're going to check our work together. I think by the end of the hour, we'll still have a little time to do it. I'm really pleased. You guys are pretty quick with this stuff. This group must be pretty good in math for us, too. And folks at home, if you can't see, it's 22, 25, and 21 are the 3 resistors. And when you do, try and show work so I can see what you're doing, so I know where you're getting the numbers from. Good. Yeah, that's right. For the series, you just add them up. And actually all add up to 220, the amps when you get all done. Not 220, sorry. Yeah, that's the voltage, never mind. I can't mark because I don't know the answer to that.
So basically, you just like wait for people over, you know, blocking the other side of the Detroit. Form sort of like Detroit. You get it? Michigan.
I just, yeah,
No. Like what?
as soon as, yeah.
Sure, it's like right here. It's like Detroit.
You want to leave on that last one you look at?
Oh, yeah. Yeah.
That is so big.
Smaller.
Okay, they're learning now.
If they give us money.
Ja. Bist du bei Amazing oder
How much I got to get from that? I'm pretty sure I think multiple every now. Really good.
Then can I see how to flip it on? You
No,
gotta
so
flip it,
basically
right?
you can do a shortcut at A here. So basically you do this. Wait, I gotta remember what to do. A is good.
Here it is, it's extra to
All you have
bonus
to
one.
do
So,
is add
so
the
put in,
O in your head.
actually, just beautiful. This is bad. I wonder
So
about
basically
that.
this was the.
You don't have to do the weird flipping part. Just put it after the
No, this is what you need to do.
Yeah, just
Skip
skip
the
that.
entire.
Throw some homes out and then you're done. Okay, folks, I'm gonna go ahead and start because I know we're running short of time. Here we
Well,
go.
then you have to like try to do actual.
Okay, so-
one over that.
Focus up here just for a sec. Here we go. Check it out. Let's look at the one. Inessa did looking good. She's dropped in all three of the numbers, and then she already calculated out one over that, and she changed them all to decimals. And got 0.133, and then she flipped it, whoop, and got 7.5 basically ohms for the total resistance. And again, 7.5, it's less than all three of them. Should be, because we have lots of pathways for the electrons. Looking good. Then from Felix, here at the top of the next board, we've got, to get the total, he's got 220 volts, so V over R, and so 220 volts divided by our answer for RT, 7.5, and 29.33, let's just call it 29. That's probably more accurate. 29 amps, a lot of current once again. And Isaac, sorry to rush you there, but you did good. Let's take a look. He's got a statement at the beginning. The voltages are all the same. V1, V2, V3, they're all 220 volts. Each pathway has the same voltage. Beautiful. Then finding each current separately, so it's V over R1 and 220 over 22 amps, so got 10 amps there. For the second one, 220 volts over 25 ohms for 8.8 amps, and the third one, he subtracted here to find 9.8 amps for the third, because he knows they all got to add up to 29. Let's see if that kind of works. That's close to 10, 10, 9, 29. Beautiful. Beautiful. You could have used the formula and found that the third one also via the formula. Questions from online folks or from any of you? That's what I would do, Ethan. Just round it. Yeah, just round it. Again, like I said, 10th grade, I'll teach you how to round if I have you again. But more or less, a couple spots is fine. These all look good. 29 is reasonable. 7.5 is probably reasonable for that one. Just a couple of spots. Yeah? All right, you've done good. When we get to combination, maybe we'll get to a combination once I see you again. But the next time I see you will be in the lab on Monday, June 7th. And we're going to call it, take a break right there. Folks at home, thank you very much. We're going to end our video right there. Thanks everybody for participating, and adios.